today's colloquium, we're happy to have Nicolas Tholozan from CNRS and École Normale Supérieure, who will tell us about Teichmuller theory and higher.
So first of all, I'd like to thank you for the invitation. I'm delighted to give this talk today and to talk about Teichmuller theory, which is an old theory, higher Teichmuller theory, which is more recent, and in the end I will mention a Foliated Teichmuller theory and how it could be seen as containing all the higher Teichmuller theories. So let me start with a background on classical Teichmuller theory. And so I must say it's the first time I'm giving a colloquium talk. And I don't exactly know what it implies, but I guess it implies quoting a theorem that is 200 years old. So I thought I would start with this famous theorem of Gauss that tells you that a conformal class of Riemannian metrics on a surface and a holomorphic structure, so an atlas of charts with values in C, are essentially the same thing. Because so if you have a complex structure, then you can look at the space of Riemannian metrics for which the multiplication by I on each tangent space is an isometry, and this is a conformal class. And conversely, the content of the theorem is that conversely, if you have any Riemannian metric on a surface, there is an atlas of complex charts in which these metrics become conformal. So this is the starting point of the study of Riemann surfaces. And then about 100 years later, the global uniformization theorem of Poincaré and Quebec so drew an end to a long history, but okay. Anyway, so this theorem tells you that if you have a closed surface, which is not a sphere, a torus, or a cylinder, then any conformal metric on it, so locally the conformal metric is modeled on C, but globally it's better, it's modeled on the hyperbolic plane. And so the theorem tells you that there is a unique complete metric of constant curvature -1. So there is a whole history to this theorem that I'm not mentioning here, but I would like to advertise for this book, which is a French book that has recently been translated in English. So uniformization of Riemann surfaces, revisiting a 100-year-old theorem that comes back on the history of the Poincaré-Quebec theorem. Okay, so I would be interested in Riemann surfaces which are topologically a closed surface of genus G, and I want to exclude the torus because the torus is not covered by the hyperbolic plane, so of genus greater than 2. And following the Poincaré uniformization theorem, you have bijections between the following spaces. So the Teichmuller space of complex structures on sigma modulo isotopy. Because in each complex structure you have a unique hyperbolic metric, this is also the same as the space of hyperbolic structures or hyperbolic metrics, metrics of curvature -1 on sigma modulo isotopy. And once you have a hyperbolic metric on a closed surface, the closed surface is identified to a quotient of the hyperbolic plane by a discrete subgroup of isometries. And so you get an identification of this space with a certain space of Fuchsian representations lying inside the character variety of the fundamental group of sigma into the Lie group PSL2R, which is the group of orientation preserving isometries of the hyperbolic plane. And so these are three ways of seeing this Teichmuller space. And let me first give a bit more details about the space of Fuchsian representations. So this character variety in general is defined for any let's say semi-simple Lie group. You can define the character variety as a space of homomorphisms of the fundamental group into a Lie group G, modulo the action of G by conjugation. And if you want to make things, make the quotient to be Hausdorff, you need to put a double quotient here, which is, comes from geometric invariant theory, but mostly it's just quotienting by a conjugation. And so in the case of PSL2R, there is a rather nice description of this character variety. In particular, so there is a notion of Euler class of representation into PSL2R, which is a topological invariant associated with this representation. It's an integral number which by Milnor-Wood inequality takes values between 2 minus 2g and 2g minus 2. G is the genus of the surface. And it's continuous, so it takes one value on each connected component. And actually, it classifies the connected component of the character variety. This is due independently to Goldman and Hitchin. Inside this character variety, the space of Fuchsian representations, the ones that arise from hyperbolic metrics on the surface, is exactly the space of representations with extremal Euler class. So Euler class 2 minus g or 2g minus 2. So in this picture, this inclusion here is better than simply an inclusion. It's a connected component, actually. So there is a subtlety that there are two components of extremal Euler class, and they are identified by, if you conjugate, by an orientation reversing isometry. So essentially, one of them is the Teichmüller space. Okay. So this Teichmüller space turns out to have a very nice geometry, and that's partly why it's such an interesting space. So what kind of geometry does it have? So this started with the work of Teichmüller. So Teichmüller was really looking at the complex Teichmüller space, the space of conformal structures. And so what it did was study basically the notion of a quasi-conformal map between complex structures, which are maps that do not distort balls too much. So if you have two conformal structures, you want a quasi-conformal map to have a, let's say, if it's C1, it has a differential which can deform a ball with stretching one direction and contracting another one. But the ratio of the stretching and the contracting parts will be bounded. So this would be a quasi-conformal map. This bound on the ratio is a quasi-conformal distortion. And a theorem of Teichmüller tells you that there is a unique map between two Riemann surfaces, isotopic to identity. If you have two complex structures on a Riemann surface, the identity is isotopic to a unique map minimizing the quasi-conformal distortion. Locally, this map is really in local coordinates, and outside a set of singular points, it has a form xy goes to kx, k minus 1 y, with k a constant. And this constant is the quasi-conformal distortion. Its logarithm is what you call the Teichmüller distance between the two complex structures. And so elaborating on Teichmüller's work and further developments by Alfors and Bers, you get the following description of Teichmüller space. First of all, it's homeomorphic to R to the 6g minus 6. So it's contractible. It carries a natural complex structure, and you can describe the cotangent space to a point in Teichmüller space as the space of holomorphic quadratic differential. That is a tensor on the surface which is locally of the form phi of z dz squared, where phi is a holomorphic function. And actually, you can say even more about the holomorphic structure. So by using Bers' embedding theorem, you get that Teichmüller space is biholomorphic to a bounded domain in the space of a quadratic differential. And this is true for any choice of a base complex structure on sigma. And when you have a bounded domain in C in a complex linear space, you can define its Kobayashi metric, which is a metric that basically measures how much how to say this. Okay, so it's a metric that measures how you can embed H2 hyperbolic planes inside your complex domain. So if you have a point on a tangent space and a tangent vector here, and a map from H2 to your bounded domain, which is holomorphic, sending a unit vector here to a vector here, then the norm of this vector for the Kobayashi metric is less than 1. That's how you define it. And actually, the Teichmüller metric, so the metric derived from the distance that I defined before, happens to be the Kobayashi metric. So it's reasonably nice and natural Finsler metric on this complex manifold. It's not a Riemannian metric, however. And so there is another geometry on Teichmüller space, which comes from the Weil-Peterson theory, which defines this time defines a Riemannian metric on Teichmüller space. So the Weil-Peterson metric is defined basically by measuring the length of a cotangent vector. So cotangent vector is a holomorphic quadratic differential. You can measure it and create a Riemannian, so a Euclidean norm on the space of quadratic differential using, but to do this, basically you need a choice of a metric in the conformal class. And the natural choice to do is to choose the unique hyperbolic metric in the conformal class. So basically, you measure pointwise the norm of your holomorphic quadratic differential with respect to this hyperbolic metric, and then you integrate on the surface. And this defines a Riemannian metric, so a Euclidean metric on each cotangent space, and therefore a Riemannian metric, which has many nice properties. So first, it's a Keller metric, as proven by Alfors. It is negatively curved. So Alfors proved it for a holomorphic sectional curvature, and then Tromba and Wolpert for all the sectional curvatures. And one drawback of this metric is that it's not a complete metric. However, it's geodesically convex, which is nice. So between every 2 points, there is a unique Weil-Peterson geodesic. And it's better, the completion of the metric is quite well understood also. Okay, so this is all what I wanted to recall about Teichmüller theory. And now let me turn to higher Teichmüller theory. So what is higher Teichmüller theory about? So first, let me come back to the 3 points of view of on Teichmüller space. The third one is looking at Teichmüller space as a subspace of a character variety, a connected component in the character variety in PSL2R. And so the basic question of higher Teichmüller space is, can you generalize this picture replacing PSL2R by another Lie group? So what sense would it make? So to give it sense, let's take a G semi-simple Lie group. So recall that this character variety is the space of representations of the fundamental group into G modulo conjugation. And then you can ask the following question, and if you answer them, somehow you create a higher Teichmüller theory. So first, are there connected components in this character variety which contain representations that look like the Fuchsian representations? So is there an analog of the component of Fuchsian representations into these character varieties into other Lie groups? So the second question would be, so this space of Fuchsian representations appears in Teichmuller theory because it parameterizes the space of hyperbolic structures on the surface and therefore of conformal structures on the surface. So if you have such a component, does this component parameterize a space of geometric structures or holomorphic objects on the surface or maybe on a manifold associated to the surface? And the third question would be, does this component carry a nice geometry? Can you create something as nice as the Teichmuller geometry or Weil-Peterson geometry on the Teichmuller space? So basically, I want to discuss these three questions. And so I will start by giving answers to the first question. So which would be the analogues of Teichmuller space in character varieties in other Lie groups. And so one possible answer is this space of Hitchin representations. So what are Hitchin representations? So these would be representations in PSLN R. So start with a Fuchsian representation, so discrete and spaceful representation of the fundamental group of the surface in PSL2R, and compose it with the unique irreducible representation from PSL2R to PSLNR, which is unique up to conjugation. This gives you a representation into PSLNR, and then you can look at the connected component of the character variety containing this representation. What is not obvious at all, for instance, is that this connected component is not everything. It's not all the character variety. And it's actually a theorem of Hitchin. So Hitchin proved, among other things, that he classified the connected components of this character variety, and he showed that this component is distinct, for instance, from the connected components that contains representations into SONR. And he also showed that this connected component is homeomorphic to r to the 2g minus 2 times n squared minus 1. So if you take n equals 2, if you take n equals 2, you recover r to the 6g minus 6. You recover actually the Teichmuller space. You get the Teichmuller space, and you recover the topology of the Teichmuller space. But in what sense can you say that these representations are similar to Fuchsian representations? So when Hitchin proved its theorem, he asked the question whether these representations had any geometric meaning, had any similarities with the Fuchsian representations, for instance. And the answer came later with this work of Labouri, where he proved that Hitchin representations, among other things, are discrete and faithful. But there is much more content in his theorem. Basically, he introduced the notion of Anosov representation, which are representations of surface groups with very nice dynamical and geometric properties. And he proved that Hitchin representations are all Anosov. So they share many similarities with Fuchsian representations, much more than being discrete and faithful. For instance, there are quasi-isometric embeddings and even better quasi-isometric embeddings than quasi-Fuchsian representations, for instance.
So sorry, this is n arbitrary or is it dimension of sigma?
N is the dimension of the G is the dimension. Sorry, G is the genus of sigma, and N is the dimension in PSLN R. Okay, so you're looking at linear representations in dimension N, and as N grows, this character variety grows.
So N can change. So N.
Yeah, N changes.
So it's any N. Right?
Yeah, it's any N, probably bigger than 2, bigger than 1. Okay, so this is one possible higher Teichmuller space, this connected component in the character variety in PSLNR, consisting of discrete and faithful representations and homeomorphic to a nice vector space whose dimension depends on the genus of the surface and the dimension of the linear representations you're considering. So there is another family of higher Teichmuller spaces that you can consider, which come from when you look at Lie groups of Hermitian type. So when you have a Lie group G, a semi-simple Lie group G, you can look at a maximal compact subgroup K. The space G mod K is the symmetric space of the Lie group. It's a Riemannian symmetric space of non-positive curvature. And G acts on it by isometries. Well, sometimes this symmetric space carries a natural Kähler metric, which is G invariant. And this is the case basically for SP2NR, SUPQ, SO2N. I think these are all the infinite families of Hermitian groups. I'm not sure. So you can think, for instance, of SP2NR if you don't like this notion of Hermitian type. And the point is that when you have a Lie group of Hermitian type, then you have a notion of Toledo invariant, which is a function from the character variety to Z, to integers. And this function generalizes the Euler class for representations in PSL2R. So, for instance, one way to define them is, so if you have a representation rho from the fundamental group of sigma into G, you can take a smooth equivariant map from the universal cover of sigma into the symmetric space G mod K. And now on G mod K, you have this Kähler form omega. You can pull back the Kähler form omega. You get a 2 form on the universal cover of the surface. But if F is equivariant, this goes down to a form on the surface. And you integrate it on sigma and maybe divide by 2 pi. I don't know. And this way you get which is the Toledo invariant of the representation rho. So you have this Toledo invariant. It's a continuous function with integral values, so it distinguishes connected components of the character variety. There is a Milnor-Wood inequality for the Toledo invariant, so depending, if you normalize things well, you can prove that the Toledo invariant is bounded in absolute value by 2G minus 2 times the rank of G. And now you can look at representations whose Toledo invariant is maximal, so achieves this maximum in this Milnor-Wood inequality. And a theorem of Berger, Yossi, and Wiener tells you that representations with maximal Toledo invariant are discrete and faithful. Again, actually, they are Anosov in the same sense as Hitchin representations being Anosov. And this is not completely trivial. Know that if the Lie group G is SUN1, so this is the isometry group in that case, actually, maximal representations into SU1. You don't get anything interesting. Anything new in SUN1, but for other Lie groups, you can actually have maximal representations which are Zariski dense, so which are not contained in a proper subgroup. This is the case for SP2NR, SUPP, and SO2N, for instance. So, okay, are there questions about these maximal representations?
So if you have a maximal representation, you get this discrete guy. You can, I guess, P2NR, you can quotient out by the Ziegel upper half plane. What do you get?
You could quotient by?
The Ziegel, so the symmetric space is the Ziegel upper half plane. So you take the quotient, you get some.
Yeah, you get some manifold. Some manifold.
Is it compact?
It's definitely not compact. It's only going to be compact for 2 R of, for instance, cohomological properties. The group that is acting is the fundamental group of the surface. It has cohomological dimension 2, so it cannot act properly discontinuously on a contractible space. It's more or less like the picture is similar to the picture of quasi-Fuchsian representations when you have you deform a Fuchsian representation. So Fuchsian representation is in the isometry group of H2. You deform it into the isometry group of H3. It acts on the boundary of H3 with a limit set, which is the Jordan curve. And on H3 itself, it acts properly discontinuously, and the quotient is homeomorphic to a surface times R. And here it's more or less going to be the same thing. I mean, it's going to be, the quotient is going to be a manifold which is non-compact but tame. And there are actually, even if you go to H4, it's not clear exactly what is the topology of the quotient, but I was not planning to
say
about
that
that.
Can be Zariski dense.
So the statement is more precise than that, but it's that you get Zariski dense representations if and only if the Lie group is of tube type. But yeah, so you have to.
But that doesn't mean like. You know,
this means that for SP2NR, for SUPP, and for SO2N, you get maximal Zariski dense representations.
They exist.
Yeah, they exist.
Not all of them,
but they don't exist for SUPQ, for instance. For SUPQ with P different from Q, okay. The statement is that any maximal representation is actually going to be contained in SUPP times the compact group. Okay. So this is so this gives us candidates to be in these higher Teichmuller spaces simply because these are connected components. Oh, by the way, yeah, something that I didn't mention is that so for SP4R, for instance, and more generally for so for higher rank Lie groups, maximal representations with maximal Toledo invariant are not. It doesn't don't form a connected space. They form several connected components, but you can have more than one. Right? But anyway, you get these connected components of discrete and faithful representations, which are reasonable analogs of Fuchsian representations. However, again, the point of Teichmuller theory is that the space of Fuchsian representation is also a space of geometric structures on the surface. And so you can ask again, is there some analog here? And there is an answer, there are partial answers to that. And one of the oldest comes from a theorem of Choi and Goldman that tells you that these representations, Hitchin representations in rank 3, are holonomies of convex projective structures on sigma. What does it mean? So as I said, so Hitchin representation in SL3 is a deformation of a Fuchsian representation J to PSL2R composed with the irreducible representation in rank 3. And in this case, the irreducible representation just consists in identifying PSL2R with SO21. So the group of linear transformations in R3 that preserve a Lorentz quadratic form. And so when you look at the action projectively at the action of something like that, what you see is that projectively you have this disk, which is so you have this circle, which is a projectivization of the nilpotent cone in R21. And your fundamental group here, via this representation, acts properly discontinuously on this disk. And this disk is just, it's H2, it's a hyperbolic plane, and the action is the properly discontinuous action of the hyperbolic plane. So you could draw a tiling, and because I'm a projective setting, so this is a Klein model of the hyperbolic space. So you can tile this hyperbolic space if you want by the action of J. Now, what the content of the, so no, not all the content of this. Yeah, the content of the theorem is that now when you deform continuously this representation in PSL2R, it does not preserve a circle anymore, but it preserves a convex set. And it acts properly discontinuously and co-compactly on this convex set. So it really, this picture is deformed, but the new action is essentially so the action here is topologically conjugated to the original action. And moreover, the image of this disk becomes a convex set. And and conversely, if you have a convex projective structure, so if you have a convex set with a properly discontinuous and co-compact action of the fundamental group of the surface, then the induced representation in PSL3R is a Hitchin representation. So that's Choryu and Goldman's theorem. And there have been partial generalizations of this theorem, but they are much less satisfying in some ways, but still. So more generally, Guichard, Winart, and independently Kapovic, Leb, and Porti constructed domains of discontinuity for Anosov representation. So you take a representation in the fundamental group of the surface, into a Lie group G, which is, for instance, a Hitchin or a maximal representation. And then you can find the parabolic subgroup of G and look, saying there is a good choice of a parabolic subgroup, such that if you look at the action on the manifold G mod P, there is a domain omega in this G mod P, on which the representation acts properly discontinuously and co-compactly. So in this setting, so for instance here, the Lie group that I have, the PSL3R, and the parabolic subgroup P is the stabilizer of a line in R3. So if P morally a parabolic subgroup means a group which is block triangular in some representation, and so for instance the stabilizer of a line in R3, the quotient of PSL3R by the stabilizer of a line, it's the space of lines, so it's RP2, and I'm looking at the action on RP2, and on this RP2 I have this convex domain, which is my omega, on which the action is properly discontinuous. And in general, something similar happens, except that understanding which quotients arise this way. So first, what is the topology of the quotient? And second, can you characterize the geometric structures on this quotient that are exactly coming from these representations? This is a complicated question that hasn't been answered yet in general. There are some ongoing works of Guichard, Winart, joint work with Brian Collier, Toulis, and all these people, lots of works aiming at studying the space of geometric structures that you get when you do these quotients and when you deform the representation. So in this aspect, these higher Teichmuller spaces generalize the Teichmuller space because these representations arise as holonomies of geometric structures, or they come from geometric structures on manifolds. Okay, and so now let me turn to my third question, which was, can you put a nice geometry on these higher Teichmuller spaces? And so here are first two things that you can say on the higher Teichmuller space, which are actually true for all character varieties. First fact is that the character variety of a surface group into a semi-simple Lie group carries a natural symplectic form. And I'm not the word natural a lot in the sequel. I'm not being precise about what I mean by natural, but one thing which is natural is that on these character varieties you have an action of the mapping class group of the surface, so the space of automorphisms of the fundamental group. This acts on the character variety. An object which is natural should be invariant by this action. Okay, so there is this symplectic form, which is invariant by the mapping class group. This is pretty nice.
Is it even obvious that it's even dimensional?
It's I don't think it's completely obvious, and I'm wondering if it's not a consequence of that. But
It's a consequence of that, but this seems like
I mean, either it's a consequence of that, or it's a consequence of the fact that conjugacy orbits in the Lie group G are even dimensional, which is a consequence of the fact that they have a symplectic form, basically. So, yeah, I think it's not obvious, but it's true. Basically. We can, I can argue about that later, but it's true. Most of the conjugation orbit, maybe. Okay. So this is a natural geometry that you have, but you only have the symplectic form. It would be nice, for instance, to have a complex structure such that the symplectic form is scalar, but this is not completely, this cannot exist in general. What exists is there is a complex structure that you can put on this character variety. You can actually see them as complex varieties, even when importantly, even when the Lie group is a real Lie group. And this identification comes from Higgs bundle theory. And it's pretty nice, but the problem of Higgs bundle theory is that this identification depends on the choice of a complex structure on the Riemann surface, or on the surface sigma. So you start with the Riemann surface structure. If you change the Riemann surface structure, you change the complex structure on the character variety. And in particular, this complex structure is not mapping class group invariant. So it's not very natural. Okay, so these are things that you have on any character variety. Now you could hope to have something better on these higher Teichmüller spaces. And something better would be, for instance, the following. So if you have a natural choice of a map from, say, a component in the character variety to the Teichmüller space of sigma. So for each representation, you have a choice of a complex structure. Then, so again, here basically you have this complex structure that depends on the choice. Complex structure on the character variety depending on the choice of a complex structure on the surface. Here, if you have a choice, if you had a canonical choice of a complex structure, then you would get an almost complex structure on the character variety, which would be adapted to the Goldman symplectic form. So the Goldman symplectic form would be an almost Keller form. And this complex structure, hopefully, may be, in some cases, integrable if you made the right choice of a natural map. So there is an ongoing work of Andy Sanders where he makes this picture really precise. Okay? But let me give an example where this is known. And so again, this is known for Hitchin representations in rank 3. And it's a theorem of John Loftin and Labourie, that the Hitchin character variety in the rank 3 is homeomorphic, so naturally homeomorphic, to a bundle over the Teichmüller space with fiber the space of holomorphic cubic differential. So I have a map from Hitchin 3 into the Teichmüller space of sigma. And the fiber over a point in the Teichmüller space, so over a sigma with a complex structure, is the space of space of holomorphic sections of so holomorphic with respect to the complex structure of the canonical bundle to the power 3. So again, it's just something of the form phi of z dz cube. Okay, so if you have such a tensor on a Riemann surface, this is a holomorphic cubic differential. And this, you have a fibration, so you can look at the bundle over Teichmüller space such that the fiber at each point is the space of holomorphic cubic differential on the Riemann surface corresponding to this point. And this is the Hitchin character variety in rank 3. And this this parametrization really comes from somehow from this picture. Basically, funny because I see John saying, doing yeah, and Brice is okay. Yeah, just argue between yourselves. Okay. It's maybe not, yeah, maybe it's not, no, okay, the complex structure of ND is not exactly the same one.
Wait, that one's not mapping class group invariant, is it?
Yeah, of course it is.
It is?
Yeah. Okay, so, maybe it's not the same one as the one constructed by Sanders, but it comes from this philosophy that if you have a choice, so basically what happens is, so what is this vibration? Let me say one word, basically. So Hitchin representation in dimension 3 divides the convex set. And on this convex set, you have a natural Riemannian metric, which is invariant by the action, by the group of automorphisms of the convex. This Riemannian metric is called the Blaschke metric, or affine metric sometimes. Okay, and so the Blaschke metric gives you a natural conformal class on the surface associated to any Hitchin representation. So this is the vibration. And once you know the conformal class of the Blaschke metric, if you want to recover the divisible convex set, what you need is the peak form. And this all comes from affine geometry. And the peak form is a tensor of this form. So you get this parametrization. And another point of view on this parametrization is really that if you fix any complex structure on sigma, then you have this Hitchin parametrization of these components by the data of quadratic and cubic differentials on this fixed complex surface. And here what you're doing is that you're varying the complex surface and taking the quadratic differential to be 0 at every time. But so let's just say that basically each fiber of the parametrization of each fiber of this vibration is the Hitchin parametrization of the character variety with respect to the given by the vibration. So it's really, yeah, I have, have this complex structure that depends on the choice of a conformal class. And I have a choice of a conformal class. And this gives me a nice complex structure, which is now a mapping class group invariant. Okay, so this picture, I should probably give more details to be clearer, but let's say that this picture has been generalized to real split Lie groups of rank 2. So I didn't say it, but Hitchin representations can be defined for any Lie group, real split Lie group. So for instance, for SP4R, and more also for Hermitian Lie groups of rank 2 by recent work of these people. And basically proving that there is this, in this situation, there is this nice way of choosing a conformal structure that gives you a structure on these character varieties, on these higher Teichmuller spaces, a structure of a bundle over Teichmuller space. Holomorphic bundle over Teichmuller space. Okay, and but there is still a lot of work to do in general to understand whether you can have a nice picture like that every time. Okay, and let me mention lastly, let me mention one other geometric object that you have on this Hitchin character variety. You have this so-called pressure metric that comes from dynamics, so the so-called thermodynamical formalism. I will maybe come back quickly on that a bit later. So this was constructed by Labouri, Bridgman, Canary, and Sambarino. So this metric, it's a Riemannian metric on the Hitchin character variety. It is natural. It is mapping class group invariant. And the nice property is that the restriction of this metric to the Fuchsian locus, so if you just look at representations that are Fuchsian composed with irreducible representation, the restriction, so you have this embedding of Teichmuller space inside the space of Hitchin representations. And the restriction of the metric to this locus is the Weil-Petersen metric. So this could be a nice or the nice generalization of the Weil-Petersen metric to higher Teichmuller spaces. But the geometric properties of this metric are unclear, and very little is known about this metric and whether it's a nice generalization of the Weil-Petersen metric. For instance, whether it is a Keller metric or whether it's negatively curved. Okay. So what I want to explain in the last 10, 15 minutes is a new point of view on this pressure metric in particular and on these Hitchin character varieties that may allow to use Teichmuller theory in order to understand these higher Teichmuller spaces. And to do that, I need to talk about foliated Teichmuller theory. So foliated Teichmuller theory is basically doing Teichmuller theory, but instead of having a two-dimensional manifold, so surface, I have a manifold foliated by, with two-dimensional leaves. And I'm looking at complex structures along the leaves. And I'm looking at the space of complex structures along the leaves. So definition, a complex structure, so I have F, a foliation of dimension 2, on a closed manifold M. And I can look at a complex structure on F, which means that on each leaf, locally, on each leaf, I have a complex structure or a conformal structure on each leaf that varies transversally. So when you move the leaves, in local charts, you change the complex structure, and you change it with a certain regularity, and the lowest nice regularity that you could ask would be continuously. You could ask it to vary smoothly also, but I will stick with continuously with the leaf. Okay. And same thing for a hyperbolic metric. Okay, if you have you could ask to have a metric of constant curvature -1 on every leaf, such that when you change the leaf, you see the metric move continuously. Okay? And for such objects, there is a uniformization theorem, which is basically the uniformization theorem of Poincaré-Quebec that you apply to every leaf at the same time. And the theorem of Kendall. And it says the following. So if I have J, a complex structure on F, so on each leaf I have a structure of a Riemann surface, then each leaf, and such that each leaf is covered by the hyperbolic plane. So it's conformal to the hyperbolic plane, not to the complex plane, nor the Riemann sphere, nor a torus. Then there is a unique hyperbolic metric on F in the conformal class defined by J. So basically, you know that on each leaf. Okay, you know that there is a hyperbolic metric on each leaf. The point is that this hyperbolic metric on each leaf will vary continuously, transversally. Okay?
So do you mean there's a unique hyperbolic metric on M?
No, on F. I mean that
What does that mean?
on each leaf. It's the same as... Okay, so I have my foliation. I have my foliation locally. My foliation is just, if I look at everything in an affine chart, my foliation is just something like that. Okay? And on each leaf, I have a complex structure. And the way this complex structure varies when I change my leaf is continuous. Then, by Poincaré uniformization, on each leaf, I have a hyperbolic structure, a complete hyperbolic structure that comes from uniformization. And the statement basically is that this hyperbolic structure will also vary continuously with the leaf. Okay? Okay, it's not, I mean, it's not obvious because it's because there is topology on the, so there is this leaf, maybe this leaf goes somewhere in the manifold, and then it comes back here, okay? And so you cannot just say, okay, this leaf is, well, I mean, you need somehow to, when you uniformize this big leaf, you're also uniformizing this one, and you have to prove that you're uniformizing them in such a way that locally they look a little bit the same. But anyway, it works, okay? So you can leaf-wise uniformize every complex structure as soon as every leaf is hyperbolic. And let me point out that, so my manifold M is assumed to be closed. And the fact that every leaf is covered by the hyperbolic plane actually does not depend on the complex structure, because if you put two leaf-wise complex structures on the same manifold, then they will be quasi-conformal, okay? Two complex structures on the same leaf will be quasi-conformal. And so if one leaf is covered by the hyperbolic space with respect to one complex structure, then it's covered by the hyperbolic space with respect to the other complex structure. So now I assume that all my leaves are hyperbolic, and meaning for one complex structure, or equivalently for any complex structure on my foliation.
You could ask, like a stronger theorem would be, that does there exist a Riemannian metric on M whose restriction to each leaf is this unique hyperbolic metric?
Yeah, so the answer would be, if things vary smoothly, then yes, because if you have a smooth, or I mean, at least if you have a C1 Riemannian metric on the leaves of a foliation, you can always extend it transversally. You can decide. You could always. I mean, you can always create a transverse direction to each leaf, and define a Riemannian metric, which is your Riemannian metric on each leaf, and something on the transversal, and decide that this transversal is orthogonal with norm 1. Okay, I mean, I don't know if I'm very clear, but I don't think it's much of a problem to extend it. There will be a regularity issue, basically, because here I'm only looking at things that vary transversally continuously. If you ask, I'm not sure about Kendall's theorem if you assume transversely smooth, but I think it's true that you will get a transversely smooth hyperbolic metric. And I mean, maybe a stronger question would be to ask to extend it so that the leaves become totally geodesic and hyperbolic, and this would be a much stronger requirement. I don't know, but I mean, extending, if you have a metric on foliation, extending it to a Riemannian metric is not a big deal. But, okay. And so now you can define a Teichmüller space for this foliation. So it will be the space of complex structures on the foliation, so leaf-wise complex structures, modulo leaf-wise isotopies. So you allow to you identify two complex structures if you can homotope one to the other one through maps that just move inside each leaf. And by Kendall's theorem, it's the same as the space of hyperbolic metrics modulo leaf-wise isotopies. And so this theory of foliated complex structures was basically introduced in a paper by Sullivan. And in this paper, he proved that this space has a nice Teichmüller geometry. Basically, you can redo Teichmüller geometry in this foliated Teichmüller space. So more precisely, there is a complex structure on this space, such that given a complex structure on the foliation F, then the Teichmüller space is biholomorphic to an open domain in the Banach space of holomorphic quadratic differentials on this foliation. And by holomorphic quadratic differentials on the foliation, again, what I mean is a family of holomorphic quadratic differential on each leaf, which vary transversally continuously. Okay? So, and again, then you can also define the Teichmüller metric, and this will be the Kobayashi metric on this space. Okay. And one very big difference with classical Teichmüller theory, however, is that the space of holomorphic quadratic differentials is infinite dimensional. Okay, and the most general statement in this setting is due to Bertrand de Roin. He shows that actually the space of these foliated holomorphic quadratic differentials is more or less always infinite dimensional. Okay, so why do I talk about that, and what's the relation with higher Teichmuller theory? So now I have to restrict to a specific foliation of dimension 2, which is the following. So I will fix a hyperbolic metric on sigma, but actually what I'm going to define does not really depend on this hyperbolic metric, but let's say that I have a hyperbolic metric on sigma. So now I can look at the space of unit tangent vectors on sigma. Okay, and on this space I have a flow which is a geodesic flow. So geodesic flow lives on the unit tangent bundle to sigma. And the geodesic flow, it's well known that it's an anosov flow, which means that along the flow, basically, there are two transverse directions, one which is contracted along the flow and one which is dilated along the flow. And so in particular, there is a foliation of this unit tangent bundle by so-called weak stable leaves of the geodesic flow. So the weak stable leaves will be the leaves generated by the direction of the flow and the direction which is contracted, like that. So other way to say it is if you have a point in your, if you have two nearby points in your in T1 sigma, and you can flow them for a long time, and if they remain within bounded distance for a long time, for every time, then you say that they are in the same leaf. And the point being that, okay. Another way to describe these foliations is the following. So you have a way to identify this unit tangent bundle with, so my surface sigma is identified with the hyperbolic plane, okay? And the unit tangent bundle to sigma, you can see it as the space of triples of points x minus, xt, x plus in the boundary, modulo the action of the group. In the following way, whenever you have 3 points in the boundary of H2, you can draw the geodesic from x minus to x plus, and then you draw the perpendicular geodesic from xt to this one. And here you have a point and a unit tangent vector, which is the vector pointing to x plus, okay? And it's easy to construct the converse of this thing and to see that this construction is completely pi1 of sigma equivariant. So this is my space, okay? And what my foliation, my weakly stable foliation is just I can look at the fibers of the map that associates to a triple the target point x plus, okay? And so this gives me a foliation on this set of triples, and this foliation induces a foliation when I quotient. So basically, at the level of the universal cover, stable leaves are all the unit tangent vectors in H2 pointing toward the same point x plus, okay? So these are my weakly stable leaves, okay? And so now let's look at this T1 sigma with this weakly stable foliation of dimension 2. And so here is a theorem. So there is a bijection between the following spaces. The space of Hölder reparametrization of the geodesic flow of entropy 1. So entropy 1, I don't have time to explain what it means, but basically it's up to scaling, these things will be of entropy 1. And Hölder reparametrizations of the geodesic flow, I just mean a new flow which has the same orbits as the geodesic flow. So it's just the geodesic flow, but moving at a different speed, a speed that may depend on the point where you are. And this different speed depends in a Hölder way of the point where you are. Okay, so this would be a Hölder reparametrization. Conjugation is just you identify two flows if one is conjugate to the other one. Okay. Okay, so you get this space of dynamical systems. And actually, it was Sullivan's idea that these foliated Teichmuller spaces should parameterize dynamical spaces of dynamical systems. The second object that's in bijection with this is a certain space of representations of the fundamental group of sigma into the space of diffeomorphisms of the circle with Hölder derivatives. I don't have time to talk much more about that, but interestingly, this space will be somehow a character variety, or at least a domain in character variety. And the third space, which is identified with these two ones, is the space of basically this Teichmuller space of the foliation, except that for things to work, you need Hölder everywhere. So you need Hölder reparameterizations, you need Hölder derivatives, and you need complex structures that vary transversally Hölder. And how does this relate to higher Teichmuller theory? Well, because that's basically the point of the Bridgman-Labouri-Canary-Sambarino construction, is that there is a way to associate to Hitchin representation certain reparameterizations of the geodesic flow. So what they do is that they embed the space of Hitchin representations into the space of Hölder parameterizations of entropy 1. And to construct their pressure metric, they just pull back this pressure metric that lives on this space of Hölder parameterizations and coming from thermodynamical formalism. But now the space of Hölder reparameterizations, you can see it as this space of foliated hyperbolic structures, which is a dense space inside my Teichmuller space of the foliation Fs. And a second theorem is the following, that the pressure metric, so this pressure metric on the space of Hölder parameterizations, is essentially the Weil-Peterson metric of this Teichmuller space of the foliation. And by that I mean, so it's not very precise yet, but if I have a cotangent vector, or if I have a tangent vector, this tangent vector is basically a foliated holomorphic quadratic differential. And you can measure, you can measure the pointwise the norm of this quadratic differential with respect to the hyperbolic metric. And then you integrate that on the T1 of sigma, and you have to know what you with respect to which measure you integrate with. But there is a preferred choice of such a measure. And then what you recover is the Weil-Peterson metric and the 1 T and 2 S's. Sorry about that. Okay, so this is very ongoing works, and there are lots of things to do in studying this Weil-Peterson metric. Does it have the same properties of the classical Weil-Peterson metric? But my hope is that this will prove useful in understanding the geometry of the pressure metric, and more generally, the geometry of higher Teichmuller spaces. Okay, so I will stop here. Thank you.
Are there any questions?
Can you go back to your theorem about the transverse Hölder structures? So, is that like an analog of Elise Cawley's theorem for Anosov diffeomorphisms of the torus? Is it like that? Cawley, she did the sort of Teichmuller space of diffeomorphism of a 2 torus.
Yeah.
And you look at the space of invariant smooth structures, and she showed that it had reparameterization. It was parameterized by Hölder structures on that.
So maybe, yeah. Probably. So somehow the theorem is not very surprising. Mm-hmm. What Sullivan did is something analogous, where instead of, so he has a different foliation. In this case, it's actually a lamination, so it's like related to the solenoid. I don't know if you know that, but a two-dimensional lamination. So leaves of dimension 2, and transversally you have a Cantor set. And he identified basically this Teichmüller space of the lamination to the space of self-maps from the circle to itself of degree 2, which are expanding. And so there is probably the same thing. So I guess, yeah, if you look at the suspension of the torus by an Anosov diffeomorphism, again, you have a weakly stable foliation. You can look at complex structures on this on the leaves, and this is probably the same as the space of Hölder reparametrizations of the flow.
Okay.
And yeah.
So with this, I guess you have kind of this theorem with each Hölder coefficient, Hölder exponent, or
I have to check that more carefully because, yeah, part of it is the Candel uniformization theorem, and yeah.
But you have it for outer for some outer. Is that?
Yeah, I think you have a if you fix a Hölder coefficient parameter here, then you will find another. I'm not even sure about that. Yeah, I'm not confident. Actually, I would really like to extend this to continuous stuff. Remove all the Hölder, because Hölder is annoying to have, because this space is not a Banach space. It's a dense, it's not a Banach manifold. It's a dense subset of a Banach manifold. But I don't know how to do that so far.
so with this pressure metric, yes, you mentioned that they embed the PSLNR, they embed that Hitchin representations into these Hölder reparametrizations. Is there some sense in which this embedding becomes dense as n goes to infinity, or anything like that? Or?
So Laborie has a paper where he tends to say something like that, but I'm not sure. I don't think he embeds things into exactly the same space. And there is so it should not be true in some sense, because these Hitchin representations have an extra property that they are. So the thing is that it depends how you embed things, and because you can embed there are different ways of embedding things depending of what you define as your length spectrum of the Hitchin representation. But the one they do in the first paper you get representations that are positively ratioed in some sense. So you have positive cross ratios. And in this, so positive cross ratios make sense also in this space. And in this space, they form a closed strict subset. So maybe a possible statement would be that when n goes to infinity, you get something which becomes dense in the space of positively ratioed foliated complex structure, whatever that means.
I mean, if n gets bigger, is there a way to relate the two, like Hitchin n representations of n plus 1? Is there?
No.
No. Okay.
I mean,
so that's the first
Hitchin n does not embed in Hitchin n plus 1, and that's an issue of all these attempts to.
You said that in the Bay-Peterson metric, you have to integrate with respect to some measure. What do you integrate with respect to?
So the point is that in these, so basically you have this reparametrization of the geodesic flow. So you have a flow on your three manifold, and it has a unique measure of maximal entropy. And you integrate with respect to this one. The point is also that in this, when I have these foliated complex, foliated hyperbolic structures, let's say, on each leaf I have so each leaf is basically H2, but it's H2 with a preferred point at infinity. So on this foliation you have two flows. You have a flow which is the flow going to this point at infinity on each leaf, which will be your reparametrization of the geodesic flow. And you also have a horocycle flow. Okay? So basically going from there to there is you have a geodesic flow. So you have a flow that preserves the leaves and which contracts transversally. On each stable leaf, it's transversely contracting. And you want to find the horocycle flow which is compatible, so which will give you an action of the affine group. And once you get this horocycle flow, then you get your hyperbolic structure, basically. And the point is that there is a unique measure which is invariant by both the geodesic and the horocycle flow. And this is what you use to prove that you get the Weil-Petersen metric.
Do you think about other Nassau flows on 3 nanovolts?
Not so far. They really come from a higher Teichmüller theory, and so I'm.
There's a lot.
I think that, for instance, so I think that this result pressure metric equals Weil-Petersen metric should make sense possibly in a more general setting, at least, for instance, for the suspensions of Anosov diffeomorphisms of the torus. But I don't know so far whether it would give something relevant. And so far I'm sticking with the surface groups and what I know, but maybe later.
Okay, well, let's just thank Nicolas again.